So looking at number 3, we're going to construct a confidence interval for a proportion here, and it gives us this information. So I'm going to go into StatCrunch. I'm going to go Stats, Proportion Stats. We have just one sample, and we have the summary information. So if we actually had, let's see, there's 1,200 people in our sample. If we actually had the results of all 1,200 people in a big spreadsheet with 1,200 rows, that's when we'd use with data. But since it's just the summary stats, we use with summary. So from our sample, there are 860 that fit the proportion. We don't have really any information here what the proportion is. Maybe it's the proportion of people who prefer vanilla ice cream, or who own a pet, or who got the flu shot. It could be anything, but out of this 1,200, 860 fit the bill. That's how many successes we had, and there were 1,200 total people. And we're looking for a confidence interval that's 95% confidence. We actually have that already set as 95. So then we hit compute. And so from our sample, if those were our results from our sample, we can be confident that the entire population, not just the 1,200 people, but the entire population would have a proportion somewhere between this lower and upper limit. So let me just show you one more thing here. 860 out of 1,200 is going to be right in the middle, because we're basing our lower and upper limit off of our sample. So 860 out of 1,200 is just over, or 71 points, I'll just leave it at 71.67%, or as a decimal, 0.71666. So 0.716666 is right in the middle here of our lower limit and upper limit. And we're 95% confident that the real proportion of all the people, not just these 1,200, but of all the people, is somewhere between this lower and this upper limit. And when you type in those lower and upper bounds, make sure you round to 3 decimal places, because the problem's just being specific there. It wants 3 decimal places. For number 6 here, we want to figure out what size sample we're going to need to get an estimate that is within a certain range, and we're confident that it's within a certain range, and it gives us the level of confidence. So if you look in your textbook, page 435, it shows you the sample size needed for estimating the population proportion. And it gives you the formula here that you're going to use. And the first formula here, it has where p hat is a prior estimate of our population proportion. And that's what you're going to see here with part A, is we have a previous estimate. So we're going to use that first formula because we have a previous estimate that it's going to be close to 0.32. And I'm just going to use Excel to solve this because it's a great calculator. And so I've copied the information down from the problem. And then let's look back at our actual formula here. There we go. So we want to take the size of the sample we need. We're going to take our previous estimate and multiply it by 1 minus our previous estimate. So we're going to do 0.32 here times 1 minus 0.32. And you could see what that comes out to, or you could just continue to string the formula along and write it all together. I like to break it up in little chunks just to make sure I'm not, if I type too much at once, it's easy to make a typo. But so I've done that first part, p hat times 1 minus p hat. And now I'm going to do the second part, and I'll put it all together. So you see next in the formula is the z of alpha over 2. So alpha basically is how much we want there to be in the tail. So if we're 95% confidence, there's going to be 5% likelihood in the tails of our distribution. 95% is in our confidence interval. There's 5% in the tails. Well, it's divided by 2 because there's 2 tails. So we actually want to find the cutoff the cutoff numbers for our distribution that are going to put 2.5% in each tail, because 2.5% in each tail is 5% total in the tails. So if you use the normal distribution, the inverse of having 2.5% in the tail, it gives you the critical value for that. And that's what we're looking for here on top, the Z alpha over 2. And it gives you, Excel always gives the -1. I'm just going to do it to 2 decimals. And by symmetry, the positive 1 would be positive 1.96 instead of negative 1.96. But those are the critical values. Beyond those Z values, there's only 5% total in the tails, 2.5% on each side. I'm supposed to divide that by our margin of error here that we want, and we want it to be 0.02. So what I'm going to do here is 1.96, and I'm doing parentheses because we have parentheses down here, divided by 0.02, and I want to square that whole thing. And so that's this portion right here. And the formula says to multiply everything together, so I need to take my results and multiply those together. So we'll get our final answer here. Our first result multiplied by our second result. And again, I broke that up into steps, but you could string that all together in Excel if you wanted to just write it all at once, but I think it's easier to break it up into chunks. And so you get this is how big your sample size needs to be. Now you can't have a fraction of a person, so you need to round that up to 2090. And it reminds you here, round up to the nearest integer. And part B is if you do not have a prior estimate and it's almost exactly the same, but instead of using your prior estimate here in the formula and doing this beginning part, you just do 0.25 there. So instead of doing any of this work with our prior estimate, we would just write 0.25 there. And the reason we do that is 0.25, you'll notice it's bigger than this number. 0.25 is the biggest value you can possibly get if you take a prior estimate and multiply it by 1 minus that estimate. So because we use the biggest number possible, it's going to make our sample size even bigger because we're using a bigger number. And so our sample size is definitely going to be large enough because we make it even bigger than what it would ever be if we had a prior estimate. So this is kind of just a safeguard. We'll use the biggest value possible here, and we'll know our sample size will be large enough. So that's why we use 0.25. For number 12 here, we're looking at a mean. So when you're looking at a mean, you're either going to use Z if we have, well, the Z table, normal distribution, if we had the population standard deviation. If we don't have the population standard deviation, then we have to use the t distribution. And it doesn't tell us a population standard deviation, so we're going to use the t distribution. So coming into StatCrunch, see if I can just lower it here a little bit. We're going to go stat t distribution, our t stats here. We have one sample, a sample of 80 patients, it says. And we have, again, the summary. We don't have a list of all 80 patients and what the results were. We just have the summary data, which is the sample mean, 5.6 days. Another summary stat is the sample standard deviation, 15.2. Oh, sorry, 0.2. And then the sample size was how many people were in our sample, so 80. And then StatCrunch will do all the work for us. We want a confidence interval, was it 95%? Yep, 95%. And when you hit compute, so our sample mean is going to be right smack dab in the middle of our confidence interval. This is our point estimate or our guess for the entire population. We're making our guess based off of our sample. But then our lower bound will be a little bit below 5.6 and our upper bound will be a little bit higher than 5.6. So here it is, 5.6 is right smack dab in the middle of our lower and upper limit, but we're 95% confident that for the entire population, the mean incubation period will be between that lower and upper limit. For number 13, we actually have a table of data. We're going to want to open that in StatCrunch. Now again, we don't have a population standard deviation. And We're looking here for the mean, right? The following data. It doesn't specifically say you're looking for the mean, but that's what we're looking for here. We don't have any sort of proportion going on. We're just looking for the mean home price with this data. So T-stats, one sample, and we actually have data this time. Here's our list of data. We got to select our data. It was in the column called var1, variable one. And so now selecting that, StatCrunch behind the scenes will calculate the sample mean and the sample standard deviation. You inputted those for problem 12. Here, StatCrunch is going to actually just look at your data and come up with those values on its own. And we want our confidence, was it 99%? So change that to 99. And now we're going to hit compute. And so the mean from this sample is smack dab in the middle of this. It tells us the mean right here. So if you average all those numbers, you get the mean. It's smack dab in the middle. But we're 99% confident that for all the homes, not just this sample of homes, for all the homes, the mean price is somewhere in between this range. Now, part B asks you to get rid of the outlier. So if you look at these homes, they're all in about 100,000s to 200,000s range. This home is way above. This is an outlier. So if we would delete that home, remove that weird home, that outlier home from our data, recalculate, we will get some different results because now, because that home was throwing everything off because it was way overpriced compared to the neighborhood. So now if we do T-stats, one sample with summary, oh, sorry, we don't have the summary. One sample with our data from variable one. Now we want our 99%. So you see our sample mean now is a lot lower because we threw out that home that was super expensive. So the sample in general are much smaller. And then you'll see our lower and upper limits are actually even closer to the mean than we had before because there's not as much variation over here. We got rid of that outlier that was throwing everything off. Look how high the standard deviation is here compared to here. Remember, standard deviation is how spread out the data is. So you get rid of that outlier that's way far away from the data, and the data is less spread out. So we're more confident. We can be 99% confident now with a much smaller range that the mean price for all the homes is somewhere between this range if we get rid of that one outlier.